it takes water to do crops, doesn't it?
Sorry that you're noisy, but I guess you'll just have
That's
to
okay.
gather them in.
Yeah,
If I had
yeah.
a cowbell, it would help, right?
Yeah. Well, thanks a lot for the introduction. And it is a pleasure to be here today. Give everybody a chance to sit down. So I'm going to be presenting today on climate change in Pennsylvania, but also kind of focusing on the Northeast. I've given this talk now, on the order of maybe 15 times. I gave it first a couple of years ago at the Pennsylvania Association for Sustainable Agriculture, PASA, and I've been kind of updating it throughout. The last time I gave this was the Keystone Crops and Soils Conference, which was held in Harrisburg. So I've updated some things since then, so I'm looking forward to kind of sharing with you guys and everybody here, some of the interesting trends that we're seeing in terms of climate change, looking from the past through the present and into the future. So just thinking about water extremes, I've got a picture here from our experimental watershed. This is a weir actually that measures stream flow in our Mantango Creek experimental watershed, not too far from Klingerstown, Pennsylvania, which would be about 40 miles north of Harrisburg. I can just flip through a couple of the images here to kind of show you the kind of water extremes that we get, from flood. That first picture was actually from Tropical Storm Lee. This is a really dry period, and then back to high flow. So it's these kind of water extremes that we get, from either really high flows and lots of rain to dry conditions, and that's kind of the challenge, that we all face in trying to deal with these different kinds of extremes. So I've divided this talk into basically 4 parts. The first part just looks at kind of the big picture. They're looking at national climate assessment. So the U.S. does every 4 years or so, does a national climate assessment. They're actually in the middle of doing one right now that should be out later this year in 2018. So I'll be looking at some of the most recent trends that have come out from the national climate assessment. Then I'll focus in on results from work that we do in our own experimental watersheds in Mantango Creek. So this is the watershed where myself and others from my lab where we work near Klingerstown. We looked at about 45 years. I've updated these now to about more like 50 years of trends, stream flow, precipitation, temperature, seasons, things like that. So I'll share with you some of the things that we're seeing in East Central Pennsylvania. I've got projections to share for the Northeast, so I'll share some kind of projections for the middle of the century to how things are likely to change as long as carbon dioxide emissions continue on their current trajectory. And I'll close with a little bit of info on where you can go to find climate forecasts online, like seasonal forecasts, things like that, and decision support tools and things that could be helpful as you kind of make decisions in the near term all the way out to maybe a year or two in advance. So we'll start big picture. So the warming of the planet, it's pretty unequivocal. This is just showing, this is the trajectory of carbon dioxide concentrations in the atmosphere. We were about 290 parts per million back in the late 1800s, just around the dawn of the Industrial Revolution. And we've increased now to about 407 parts per million in 2018. That's a 40% increase over that time span. And this just shows the changes in temperatures in response to all that CO2 that's in the atmosphere. You can think of carbon dioxide like a blanket. When you go to bed at night, you put a blanket on, and the more blankets you put on, the warmer you get. Well, CO2 is kind of like that blanket. The more CO2 we put in the atmosphere, the warmer it gets. And you can see the temperature anomalies, getting up to about, we've warmed by about 1 degree Celsius already, just shy of 1 degree Celsius. That's just 1 point something degrees Fahrenheit. This is the only graph I have in Celsius, so this is the only one I was unable to convert. You can look much further back in time if you really want to see how unique our situation is. So this is going back 800,000 years. This is using data from ice cores from Antarctica. And this just shows the trajectory of carbon dioxide concentrations in the atmosphere. And you can see for the most part, until recently, we've never really gotten above 280 parts per million until, just the last 100 years or so. And recently, about 1950, we started on our upward trajectory. Actually, we were on our way down. This was actually, CO2 concentrations will start to go down. These are, these high periods here. These are interglacial warm periods. These periods here would be, ice ages. So, this kind of waffling of CO2 kind of controls the climate's thermostat. So in 2018, here we are at 407 parts per million. That is the highest CO2 concentrations we've had in about 3 million years. So you have to go all the way back to the Pliocene to find carbon dioxide concentrations as high as they are today. And so the response to that, with all that CO2 in the atmosphere, has been, record-breaking warm temperatures that we see globally. So this is just a chart showing all the record warm years we've had, and just kind of as they've increased all the way through 2017. This chart was put together by NASA. So you can see even 2017, not an El Nino year, but also record warm. 2016 was the record warmest year we've had, and it was influenced by an El Nino. So even though, like I said, even though 2017, this past year, was not influenced by an El Nino, just so you're aware, is these conditions up here when you have really warm sea surface temperatures in the Pacific, and that usually means warmer temperatures globally. When you have La Nina, which is shown here below, these are cooler than normal temperatures in the Pacific, and that usually means a little bit cooler year than normal. So El Ninos tend to drive a little bit of extra warming. And this is a really nice graph that the New York Times put together showing the trajectory of global temperatures from the late 1800s all the way through present, and then shows which years were influenced by El Nino. So you can see even 2017 without an El Nino was the second warmest year on record. So this past year, it was even record warm without the assist from the warm ocean temperatures in the Pacific. So temperatures across the US are rising. This is from the US National Climate Assessment. In fact, this is from just last fall. They published an update to all their trends. You can see nationally how temperatures are changing, mostly going up, except with some minimal changes going on in the southeast and south central, even the northeast, mostly warming. We can look at seasonal breakdowns of these things. This little chart to the right here just shows the increases in temperature differences relative to 1901 to 1960. So again, Northeast is showing warming trends. Seasonally, it looks as if the winter is actually showing some of the biggest changes in the Northeast. So these are some of the largest temperature changes we've seen actually happening in the winter, and the summer is not really warming as much. So we're not seeing a lot of the big increases happening in the summer yet, which I guess is great if you don't like extreme heat, but we've had quite a bit of warming in the wintertime. But these are the means. That's what we're talking about, average temperatures. So what happens if we're thinking about extremes? Well, the issue when you change the mean, and this is what's shown here, so you're shifting the mean to the right, it means you're also incurring the probability of more extreme heat. So that's what's shown. Just think of our climate as like this bell-shaped curve, where most of the time we experience temperatures in here. Sometimes we have extreme cold, sometimes we have extreme heat. But as the climate shifts, as it gets warmer, we shift away from cold extremes and we move into these hotter extremes. They become more likely. That's just increasing in probability. So these here are data from James Hansen from when he was working at NASA. Put together a plot for the Northern Hemisphere showing how that shift is happening, how we are shifting away from colder extremes and shifting into heat extremes that we really haven't experienced before. These are 4 and 5 standard deviations, from the mean, which, is pretty extreme. It would be, some of the heat that, you've seen in the past, 5 years or so, some of that qualifies as being extreme. And it could be even in the wintertime, but it would be just much more warmer than what you're used to experiencing. And so the way James Hansen describes our current climate is that if you think of the past climate, the climate of the mid-1900s, you would basically have two, you can think of it in terms of dice. So 2 sides white for normal, 2 sides blue for cold, and 2 sides red for hot. Well, our current climate, the current conditions we find ourselves in, we need really 4 red sides to characterize that. So the odds of rolling red, of rolling heat, of rolling extra heat are better now than they used to be. So you're more likely to see a warmer than normal day than a cooler than normal day. These are also data from the National Climate Assessment showing how record highs are outpacing record lows. This is just going by decade. And so here's the 1950s showing about 1 to 1. That means 1 record high for 1 record low. It's kind of in balance. And that's what you would expect in a climate that's not changing. You basically have about 1 record high for 1 record low. In the 60s and the 70s, there's actually more record lows than record highs. But then in the 80s, it was about 1 to 1 again. In the 90s, 1.4 to 1. 2.0 to 1 or 2 to 1 in the 2000s, and now in the 2010s, at least through 2017, it's 2.3 to 1. And in 2016, it was 6 to 1. And in 2011, I think it was 7 to 1. So we've had some extreme years where we've had extreme heat. And that, that's reflected in these ratios of record highs to record lows, another kind of indicator of a warming climate. So in response to the extra warmth, we're seeing changes in seasons. So this is just the growing season. So for the Northeast, we've seen an extension of the growing season by about 10 days. And that's typically calculated based on the last freeze date in the spring and the first freeze date in the fall. And the difference between those two would be the growing season. And I'll show you data on that from our watershed shortly. This is a really nice graph that the New York Times put together to show you spring of 2017 when it warmed up really rapidly. I was out doing field work in January and February of this year, or last year I should say. And it was in the 60s in January, and then in mid-February I was out collecting stream samples and it was like 70-something degrees. I mean, it was anomalously warm. And so this just shows the advancement of spring in 2017, and it was upwards of 25 days early this year relative to years in the past. And so this is being charted by the National Phenology Network. They look at buds on trees and other indicators to indicate the arrival of spring. So spring in some of these warmer winters is arriving quite a bit earlier. That causes plants to respond, and then it renders them susceptible to frost later. So these kind of rapid warming springs can be actually kind of a risk when you think about late season frosts. Plant hardiness zones are also shifting. So these are just showing, data from 1960 to 1989, the typical plant hardiness zones that you would use from USDA to determine, what plants are appropriate for your climate zone. Well, there's 1980 to 2009, and you've already had a little bit of a shift northward of all these hardiness zones. So they're also moving north as the winters are changing, and we're seeing less frequent cold air outbreaks. We're seeing changes in precipitation. So these are the annual precipitation amounts that that we see nationally. There's definitely increases in the Midwest and in the Northeast. We're also seeing increased rainfall. This is average annual rainfall, the average amount of rainfall we get in a given year. So that shows an upward trajectory for the Northeast U.S. More rain than we used to get throughout the year. The biggest increases are in the fall. So the fall rainfall is really going up in the Northeast. You can see it reflected here and over here. So these are the seasonal changes. As it turns out, summer and most of the rest of the seasons, not big changes in the Northeast. Not seeing big changes in rainfall in those seasons. It's the fall when we've had the biggest increase in rain over the past, say, 50 or 60 years. We're seeing increases in extreme rainfall too. So these would be events that would be greater, or the top 1% of daily rainfall events. These are events that well over a couple of inches in a day. And 55% increase in the Northeast. So the Northeast has seen the biggest increase in extreme rains. The kind of rains that cause field erosion, the kind of rains that cause issues with flash flooding, those kinds of rainfall events. So those events have gone up in the Northeast, more so than anywhere else in the U.S. so far. And you don't have to go too far back, even in central Pennsylvania, to find an event that would be considered extreme. This was in October of 2016. We had a set of training thunderstorms that just formed and just did not stop raining. This went on for 6 hours or so. I was at home, and it sounded like someone was power washing the side of my house. It was raining so hard. I've never experienced rain that hard, even myself. And so we're looking at 7 to 9 inches of rain in less than a 6-hour period for most. This is just northwest of I-99. So that I-99 corridor just west of State College got hit the hardest by these rains. And in fact, if you went up near Williamsport, these northern locales up here, they had landslides coming down the ridges from that kind of rain. I mean, just the rain was just so extreme. And so that would be, an 1,000-year return period. It's the kind of the event has like a 1 in 1,000 probability of happening in any given year. They had flash flooding in Spring Creek. This shows the flash flooding in Milesburg. It's just impossible for the soils to handle rainfall of that intensity. It's just going to run off. And so these kind of events do happen. They're happening with more regularity, and the reason for that is pretty simple and straightforward. It's just that as you're warming the climate, so you're just increasing temperature over time, it means the atmosphere holds more water. So there's this fancy physical equation. I I won't try to pronounce it for you, but it's just the essential thing that you need to know is that for every 1 degree Celsius rise in temperature, the atmosphere can hold 7% more water on average. And so we've warmed by about 1 degree Celsius, just shy of 1 degree Celsius. So that means on average there's 7% more water available for these rainstorms to tap when they come along. So every time a storm comes along, there's more moisture in the atmosphere, and it can wring that out in these extreme events. And so as you continue to warm, the risk of these extreme rains is going to go up. You'll probably get more rain, more of your annual rainfall will come in these extremes, and then you'll have longer dry spells in between. That's at least what's projected to happen. So, and that's what's starting to happen. And so, another interesting thing, it seems like it's distant and far away, and you wonder, like, why would we care about the Arctic when we live in Pennsylvania and New York and Maryland? But the extreme weather that we experience is in part due to changes that are happening in the Arctic. And the reason for that is because the Arctic is cold. It's got, this is 1984, so this white area is the extent of the ice sheet, the Arctic sea ice sheet in 1984. And so what happens is you get this really strong temperature differential between the Arctic and the mid-latitudes. So the Arctic is really cold, the mid-latitudes are warm, and that temperature differential drives the jet stream. Basically, the stronger that temperature differential is, the faster the jet stream moves. And so you get these kind of jet stream patterns that move along really quickly. It means weather systems don't get stuck. So that means if you get a storm, it doesn't hang around very long. If you get a hot, dry spell, that doesn't hang around very long. So more often than not, if the jet stream is progressive, you don't get these extreme kind of weather events. But what has happened now, and this is September 2016, here's the ice extent, so I'll flip between the two. You can see how much of that ice has melted. This is the September Arctic ice minimum, so it's the minimum sea ice extent. They measure it every fall. That's gone away. It's been replaced by blue water. So white is reflective, blue absorbs heat. So it means that the Arctic is warming. It's warming faster than anywhere on the planet right now. And so what's happening is you're decreasing the temperature differential between the Arctic and the mid-latitudes. And that means the jet stream is slowing down on average. And this has now been shown statistically, looking at trends over time. There's people looking into the physics of this. This is an active area of research. But what you get is patterns like this. They're really wavy, and it means that if you're in this kind of a pattern, you got cold and wet conditions in the east, hot and dry in the west. But the converse can also be true, where you could get cold and wet in the west and hot and dry in the east when you get these really wavy jet stream patterns. And if they get stuck, it means you get extreme weather for a longer period of time. If you're stuck in the cold and wet pattern, it means you get a whole lot of rain and it keeps on coming. If you're stuck in the hot and dry pattern, it means that you get an extended period of heat. And we've seen this, and there's been a lot of speculation about what role is climate change playing in these jet stream patterns. But here's last September, and we had a really wavy jet stream pattern that got stuck for 6 weeks almost, and we had really warm weather that extended all the way through October. September was anomalously warm, and so this is what can happen when you get a jet stream pattern that looks like this. And you don't have to fast forward too far to find December when we had another intrusion of the polar vortex to have a jet stream pattern like this. And these wavy patterns are being more influenced by the change in climate. And so it means that for people living in the mid-latitudes like here in Pennsylvania, that we could be subject to more extremes in weather because of the changes that are happening elsewhere. So just kind of an overview of some of the things that are happening. I like to show this quote from Kevin Trenberth. It's just that we've entered a new normal, or even really a shifting normal if you think about it. And that most of the weather events that we experience now really aren't the same as the ones we've had in the past. The storms are different. They're being influenced by changing conditions, warmer atmosphere, more moisture in the atmosphere. So we're kind of subject to some changing climate, and we're seeing different kinds of weather patterns than we've seen in the past. So I'm going to zoom in now. I zoom into the Mantango Creek Experimental Watershed. So since I work for USDA, we're part of this LTAR network, this long-term agro-ecosystem research network, and there's sites all over the country. There's actually 18 of them now, and we are part of the Upper Chesapeake Bay LTAR site, or our site is the Upper Chesapeake Bay LTAR site. And so we do a lot of long-term monitoring. We've been monitoring since the late 60s. And I'll show you some of the data from the watershed where we work. These are just trends that we've been looking at. And so this is this is a sub-watershed of the Mantango Creek watershed. The Mantango Creek watershed is actually quite large. It's 160 square miles in area. This little watershed, W38, where we work, is really only 3.5 square miles. So it's an area where we do a lot of intensive monitoring. We look at precipitation data. We have temperature data that began in 1978. These all go through present. I should have changed these. We've got these going through the present day, and I look at trends through 2016 instead of 2012 now. And stream flow. So we have stream flow monitoring at the mouth. So this allows us to do almost like a water balance. We can look at how much rainfall is coming in, how much water is coming out in stream flow, and we can kind of assess what's going on inside the watershed. So when we look at temperatures in our watershed, we see all the same things that other people are seeing. We see increases in the annual mean temperature. So the mean temperatures are going up by about 0.5 degree Fahrenheit per decade. We see changes in the maximum temperatures, the annual mean maximum temperature. And the minimum temperatures are going up. The interesting thing here is that the minimums are actually going up faster than the maximums. So 0.52 degrees Fahrenheit per decade relative to 0.4 for the maximums. So that's kind of reflected in some of these increases in the wintertime temperatures at night especially. There's been some research suggesting that cloudiness has increased over the Northeast, especially at nighttime. That means that your temperatures at night don't get as cool as they used to because the clouds don't allow all the radiation to escape. They keep it a little bit warmer than they would otherwise. You don't get that radiational cooling. And so there may be a role of increased cloudiness in driving some of these these minimum temperatures to rise faster than the maximums. We've seen shifting seasons. So this is basically the last freeze date in the spring. And it's coming earlier now, about 5.5 days per decade earlier. This is the first freeze date in the fall, and it's happening 4 days later per decade. And so this shows you how the growing season is expanding as we kind of move through time. So we agree pretty much with what the National Climate Assessment has shown, that there's been an expansion of about 10 days per decade of the growing season. So, back